Welcome back. Today we're going to do main memory. And one of the most essential parts of the operating system is its memory. And managing memory is one of the jobs the operating system takes care of. And in this particular chapter we're going to look at the background of memory as a concept, swapping, memory swapping, contiguous memory allocation, paging, the structure of the page table, what a page table is, segmentation, and as an example we'll look at the Intel Pentium architecture in terms of how its memory management is performed. However, you could probably take an entire course in that and actually still not learn everything there is to know about memory management in terms of the way the operating system uses it. And you might think that the memory itself, and you probably would be correct in thinking that the memory itself is the main component, because nothing's really going to run without the memory. As soon as the memory gets corrupted, as soon as we have a page fault of some sort, not really a page fault, I should say that, some sort of a memory-related error, either running out of memory or not being able to allocate it correctly, everything dies. So you might think the memory is sort of like the backbone of the operating system in some ways. So the objective of this particular chapter is to provide a detailed description of the various different ways that of organizing memory in terms of the hardware, looking at and discussing the memory management techniques, including paging and segmentation as concepts, providing a detailed description of the Intel Pentium, which supports both a pure segmentation and a segmentation with paging concept. And if you don't know what paging is, that's what you're going to learn today. If you don't know what segmentation is, I'm also going to go over that vocabulary as well, so you have a clear understanding of the terms that are also being used. So let's take a look at a little bit of the background. In terms of the concept of program, must be brought from a disk, usually stored on a hard drive somewhere, must be brought into memory and then placed within a process so that it can be run. So a couple weeks ago, maybe it was last week, talked about CPU scheduling. I believe I've already covered CPU scheduling. And in terms of that concept, in the beginning we talked about processes. So every program that gets started that runs on the operating system runs in the form of a process. A process gets scheduled by the CPU scheduler, and it gets allowed to run. And we have a little space in the kernel space called a process control block that keeps track of all the running processes and what memory locations are associated with each one of those processes, and how many CPU cycles they need, and what kind of I/O resources they're going to use, and all the information about all these various different processes are stored in this particular table. Interesting thing is that everything I just been like rambling off the last 2 seconds here is stored in memory. It's all dependent upon memory. So what we're looking at really in the big picture is a memory abstraction of all of these components that we're creating and storing, and then keeping information. So data storage essentially, and information storage and information tracking, which is how we're keeping track of our processes. Our processes are nothing more than a memory abstraction as well. So main memory and registers are the only storage the CPU can access directly. Registers are going to be the fastest form of memory because they are closest to the CPU. Not too far, not that much of a move to get from the CPU to the registers. Registers are a form of memory. In fact, we could take memory and categorize it out as RAM, DRAM, SRAM, look at cache memory. We can look at secondary storage, which is what the next chapter is about, long-term memory. We can look at registers. From a computer architecture point of view, registers are primarily used for fast processing close to the CPU. The runtime environment uses it. The runtime environment can load something into a register, basically facilitate execution in the form of a stack for which the CPU orchestrates. Everything closest to the CPU is faster. Everything farther away from the CPU in terms of memory is slower. So the farthest thing away from the CPU is the secondary storage, which is your hard drive, your USB drives. Always going to be slower in terms of access speed. And everything closest to the CPU is more expensive. Register memory is very expensive. Hard drive space, very cheap. Farthest away from the CPU, the cheaper the memory. So our RAM, our main memory, is kind of stored in between. So it's not dirt cheap. It's a little bit more expensive than hard drive space, but it's a little cheaper than registers. So it's right in the dead center, essentially. So what we've got here, register access is really quick, 1 CPU clock cycle or less needed to register an access, for a CPU to use in terms of processing time to access a register. Cache memory sits between the main memory and the CPU registers. So cache is kind of the halfway point. So we got the registers, we have the cache, and then we have the main memory. I'll call it main memory in terms of lack of a better word for it. But it's the bulk of the memory that we're configuring. So protection of the memory is required to ensure that the correct operation is being performed. In terms of protection, it's who can access it. It's which process owns it, who can access it, what can be changed about it. Is it read-only, is it read-write? That's what we're looking at in terms of the correct operation that might be performed. So we normally measure memory in terms of a base and a limit. So a pair of base and limits themselves register and define the logical address space that we're looking at. And here's a picture of memory. Why do they draw memory like this? I don't know. But you always see it in textbooks or on the internet when you do a search on memory concepts. Usually, sometimes I turn it upside down. I put the 0 on the bottom and I put the maximum address on the top to say that this space belongs to a process or something. Or to say that maybe this is all of the memory and we have a bunch of processes in this memory space. But in any case, we've got it divided out into equal chunks. Although this one on the bottom looks a little bigger, I think it's supposed to be equal chunks that are divided out per process. Some operating systems don't divide out in equal quantity. Some of them actually give more, not modern day operating systems, but some previous ones actually allocated more memory to certain processes. And not every process was created equally. And in between, to identify the process space, we have a limit and we have a base. A base is essentially the starting point or the new 0. And then the limit is how big is this block going to be? How many banks of memory are we going to store in there? And this is a complete abstraction. It has nothing to do with the physical hardware that's installed on the computer. The physical hardware is it's a physical abstraction versus a logical. So we have the binding of instructions and data to memory. Which is kind of interesting. So the address binding of instructions and data to memory should happen in 3 different stages. We have the compile time. This is what you get when you say integer I, integer f, double D, and you have all these variables that you've defined, and you've said this is an integer, this is a float, this is a double. And each one of those integers, floats, and doubles, those variables are taking up different size memory. And it's called compile time allocation or static allocation because before the program runs, as you're defining the language and as you're picking out your variables, you're defining a data type and the data type's associated with the memory that's being stored. So at compile time, if the memory location is known, it's an absolute code that's created that can be generated automatically. You must recompile the code if this location is going to change. Exactly where that memory is going to be used when you compile your program and you run it, who knows? It could be anywhere on the computer and it can change. So when you double click on an executable file and you run a program, as I mentioned before, the program is on your secondary storage normally on your hard drive. You double click on it, brings up into memory, loads it up into a process space. A process space is nothing more than allocated memory. And the allocated of that memory for that process is only used by that process. So that integer I or that float f that you created and got statically allocated at compile time is going to be in that memory area somewhere. Always. It's never going to be in somebody else's memory area. And it's never going to be in the same address. So if you haven't noticed, outside of maybe assembly language, well, I don't think you can do it in assembly language either. Every 99.9% of all modern day programming languages at a 3rd, 4th generation or maybe sometimes even lower, you never pick the memory address. It's always an abstraction that you're using of the memory address. In the case of C and C++, you're using a data type abstraction and an identifier, or the name of a variable, so I or my integer or something. And you're getting at the memory through that abstraction, which is kind of interesting. You're never going to, even when you use pointers in C and C++, you never get the memory address either if you haven't noticed. Memory address is never, because you can't, there's no such thing. The memory address doesn't actually exist. So a compiler knows where it's at, but that's part of the runtime environment, it's part of the process, because How do you know you're always going to get the same bank of memory when you double click on that program and it brings it up and loads it into a process? You might actually get a different bank of memory. So we never use the addresses for anything. So if you're not statically binding it at a compile time, you're going to do it at a load time. Load time is where you get the relocatable code. So if it's in memory, leave it and link it at load time, or load it if it hasn't been loaded. So it must generate relocatable code if memory location is not known at compile time. You don't know where it's at. Sometimes it's by file name. As an example, your DLL file, it can be linked logically. Well, dynamically linked libraries is what DLL stands for. So if you're writing a Windows program and you have a dynamically linked library that you're going to use, and it's a third-party library, well, when you load the program up, it looks for that library file, the DLL file. In fact, the entire operating system loads that way. And you notice this when you mess up the register or you delete some of the DLLs or something. And you have a missing DLL error. You don't get this until you reboot the computer, and it usually happens before the computer gets done booting. You'll get this DLL error that comes out of nowhere. You wonder, where did that come from? Well, it was a dynamically linked library, and you either removed the library itself, deleted the file, or you messed up the register so that it doesn't know where to find the file. So it's there, but it can't find it or something. That would be called a relocatable code, because we don't know where it's going to be at. We don't know where in memory. Instead, we're going to create this artificial link in the program that says go out and load it. So the last but not least is at execution time. So binding is delayed until the runtime actually occurs. If the process can be moved around, its execution from one memory segment to another, it can be done. Sometimes you need hardware support for address maps based on limit registers. So at execution time, it's really hard unless you're running in a real-time kind of environment to set the memory, because the more you can do ahead of time, the more before the program actually even starts, the sounder the execution is going to be, and the more reliable the program is going to be. But execution time programs would be sort of like Java in the Java runtime environment and the JVM. So the Java Virtual Machine is an operating system. It dynamically loads everything, even loadable code, and which is kind of similar to the dynamically linked library, except for this is dynamically linked everything. So the operating system loads up your first program that looks for your second and your third, and these programs are .class files. And so it can load at runtime files that are on your computer, files that are on somebody else's computer, can pull them from all different directions, and it allows for flexibility. So that's one of the good reasons in terms of using an operating system that's, kind of works with the compiler like the JVM. You got the best of both worlds. You got a compiled programming language, and you have a runtime, real-time interpreter working simultaneously, which is kind of cool. So here's the abstraction of what it would look like if you had a multi-step processing of, let's say, a user program or a program. Up at the top here, this is your notepad file, this is your source code file. And what this is doing is putting all the pieces together in terms of the compile time, the load time, and the execution time, the three different stages for which memory can be loaded and used in a program. And these are just generic stages as well. So here's your source code. Your source code gets compiled. So this is here. Let me make this bigger for you guys in the back, actually, so you can see what it is I'm looking at. We have source code at the top here. Source code goes into the compiler, and at compile time, that's when the compiler or the assembler is putting the things together and translating it into source code. This is really what's meant by compile time, memory management or memory loading. And then we have an object code that gets created. Then we have other object models, and these are what I'm calling the dynamically linked libraries, or the DLLs. Because what we're looking at is objects and objects and objects. And normally a linker takes all these objects and puts them together to create that executable file for you. But at load time, the linker, the linkage, is actually created while the program is being loaded. And what ends up happening is the runtime environment goes out and says, well, we need this object, we need that object, go find that one over there. So anything dynamic is loaded here. Anything static is loaded here. So this is static allocation. And what I'm trying to do is give you the vocabulary for this. Because what ends up happening is you start looking at stuff and go, well, Is that dynamic or static? And is it load time, compile time, or run time? Well, it depends, because depending upon your configuration, your use of your memory is going to be different. Here, if you have all the objects separated out, you've got load time linkage going on. And the linkage is nothing more than putting the pieces together, establishing the bridge between all the different objects. Then you're looking at a runtime support needed to load these objects. And then you're looking at the facility of loading something and putting it into memory. And a lot of people say, well, why bother? Just put everything at the compiler time up here in the source code. Why dynamically link anything? Well, here's the interesting thing. When you run your program, as an example, going back to what I said, double click on an executable file, loads up a new process is sitting out there in memory, yada yada. Well, every process is going to have a duplicate of everything. Isn't that kind of a waste of memory? So what if you loaded it up once? At the beginning of the operating system, you loaded up all these DLLs. So you only have one dynamically linked library, one of these object files that's being loaded and it's being worked with all of the other programs that use it. Then you have fewer number of odd items that are located in memory, and you're making better efficient use of the memory. If it's already loaded, why are you going to load another copy of it? Why are you going to load another copy of that? If you haven't noticed, in the more earlier versions of some of your popular programs, let's say, for example, Microsoft Word, in the old days you could load up like 5 different versions of Microsoft Word. It would be 5 different processes. If you double-clicked on it 5 times, you're going to get 5 different processes, 5 different instances of Microsoft Word. Now you only get one. You should only get one. If they haven't fixed this yet, I don't know. Why load a program 5 times? But you could load 5 Word files. And you could switch between the different Word files, but one program. Otherwise, you're eating up all your memory. You're loading it up 5 different times, when really it's just one program that you're using with 5 different files. Which is kind of the opposite, but very similar with these DLL files. One DLL file, it sits out there. And it's used for everything. Now, as an example, the print queue. On your computer, you don't have a print queue or a print concept for every single application. All applications write to the same print queue. So you only have one print queue loaded up in the memory. It minimizes the effort of having to load multiple things, but it also makes better use of the memory. So people who are concerned with their memory usage are doing this. They're doing load time dynamically linked. And I've been mentioning DLL, and to give other operating systems credit as well, it's not just a Microsoft concept. We have SOs or O's in the Linux and Unix environment. SO stands for shared object. Same thing as a DLL, essentially. It's a library module that gets loaded at load time when a program calls and uses it. So we can have the same concept essentially on different platforms. So the linker links the objects together at the load time, and then we have a loader. The loader takes the system libraries and all of the different objects and puts everything together for us and loads it all up. What exactly is loading? But for example, to load something up is to put it into memory. Essentially, it's being allocated memory. So all the really, operating systems, you can break it down to one concept. It's a memory manager. Everything, even the kernel, is memory. So when a computer turns on, kernel starts up, it gets loaded into memory, and then it loads more stuff into memory, and then more stuff into memory. And eventually user programs get loaded into memory. So the loader puts everything into memory, all these different pieces of code and stuff. At execution time or at runtime, this is kind of the last kind of step. It says dynamically linking down here, and even though up here I said, well, DLLs are kind of here too, it's the same thing. But down at runtime, after we're loading in the objects into memory, if the object isn't there, assuming that this came from another program, it came from somewhere else, dynamically loading the system library and dynamically linking it is pretty much the given task, whether it's preloaded or whether it's being loaded and linked all at the same time. It's in memory, there's some sort of binary image that's being run, and it's dynamically going out and linking to these objects that are in existence. So that's how we get the libraries essentially to be shared. Because there's really only one library object for every functionality in an operating system. And theoretically, we should be reusing it. We should be going and calling it again and looking at it and, running it without having to load another copy of it, another copy. In the old days, we had a copy of everything. We had duplicate stuff in memory. So from a non-technical point of view, that's memory management. It's minimizing what we're loading in, linking stuff in there, either at compile time, at runtime, or at load time. The other component of memory is the abstraction of the logical versus the physical. And this is what trips up a lot of brand new computer science people who aren't familiar with the concept of memory in terms of what it is we're trying to accomplish. I just realized how small that was. I'm going to make it a little bigger. I got used to the big text. Well, that's much bigger. Well, much readable. Okay. Easier to read. Although just scroll off my page a little bit. Physical memory is the physical chip that is inserted in a nice little slot on the board. Sits on the board, and it just gets used as a piece of hardware. Chip memory comes from all different manufacturers. It has different labels on it. It's supposed to be all the same. It's supposed to be all compatible. It has different speeds. There's different characteristics associated with it from a hardware perspective. Different addressing that goes on. It gets read into what's called a memory management unit, or an MMU. So the MMU takes all your memory banks that you've physically installed. And I'm sure you've seen these cards before if you've ever opened up your computer. And they even have them on notebook computers. There's usually a slot in the back of the computer. You open up the door and you see, oh look, I can put cards in there, you know. That's the memory I'm talking about. It's called DRAM, memory. So the concept is we have to make a logical abstraction of this physical memory in order to use it by the operating system. Because we can't read and write to the physical memory precisely. If we do that, we are essentially limited to the addresses we can identify and to the configuration that we identify. Instead, we don't even read it at all. We read everything from the MMU. So the operating system looks at the MMU abstraction of the memory and says, hey, you got 2 gigs. Hey, you got 1 gig. Now, this is the memory that's available to you. And the MMU creates the consistent view of that memory. That's all physical address space. So the concept of the logical address space that is bound to a separate physical address space is the central to proper memory management. Logical addresses are generated by the CPU, also referred to as virtual, because logical addresses don't really exist. The CPU generates its logical addresses based upon the physical addresses. There's a direct mapping between physical and logical. We need the physical addresses to physically store the memory. We need the logic to provide the abstraction so that we can, from an operating system's perspective, find address space to load our process in, or find something for our DLL or something. So physical addresses are seen by the memory management unit. We don't see the physical addresses. Instead, we create a logical. And logical and physical are the same in the compile time and load time binding schemes, logical or virtual, and physical addresses differ in execution time. In terms of address binding schemes at execution time, they're a lot different. They're a lot different because we have to look at it in terms of the memory management that's going on in terms of the logical perspective. Big question a lot of people come up with is, why do we have logical? Why don't we just use the physical? And then they realize, oh, well, it's because physical addresses, you can't rely upon that. They're always different. It depends on who you bought your manufacturer, who manufactured your memory. And do you think that operating system companies are going to write a special operating system for every single computer on the market? No. They're going to make a more generic approach. The generic approach reads for the memory management unit that makes everything consistent, or consistent enough for the operating system to figure it out. But here's the big catcher of the whole situation, the reason why we're using logical or virtual memory instead of the physical. Not that we could, but even if we could, we wouldn't want to do it. Because with the logical, we can make 10 times, 20 times, 2 times as much memory. And we can fill up the logical and keep filling it and filling it and filling it, map it to physical when we want to run it, when we want to use it. It increases our available memory. So you might be wondering, well, I have 5 gigs on this, or 6 gigs, or whatever, or 4 gigs. Isn't that enough? Actually, believe it or not, most operating systems take like a gig. I think Windows itself takes at least 2 gigs. And what I'm talking about in terms of the physical memory space is what it needs to adequately, in terms of speed and space, adequately be able to load everything it needs to run and get at it in an efficient way while the program is running, or while the operating system is running. So the memory management unit is giving us that abstraction so that we can create this logical comparison, this logical abstraction of it so we can fill it up and use it way past the limitations of the physical. So hardware device, MMU here is the hardware device that maps the virtual to the physical addresses. In the MMU scheme, the value in the relocator register is added to every address generated by the user process at the time in which it's sent to memory. And the user deals with the logical addresses. It never sees any of the physical addresses. So you're never going to see a physical address. It's always going to be a logical address that you're going to look at. And here's a picture of the dynamic relocation using a relocation register that's going to basically give us the offset. So here's our CPU, and here's our register, and here's our physical address in terms of the mapping that's going to happen. This is our MMU. So we might have this logical address of 346, and how it came up with that, and MMU gave us that address. Because it's going to take all this memory here, the physical address of whatever it might happen to be, and use a scheme inside of the MMU. And not every MMU does the same thing. This is just a generic approach using a relocator register. It's going to essentially give us the offset and give us the memory bank or give us some logical abstraction of that physical address. And the CPU is going to read the logical. CPU never gets past the MMU. So it just goes to the MMU, finds the information that it needs in terms of this mapping. Which means this can come from anyone. This can be, as long as it's compatible RAM, it can be upgraded, you can put, 2 cards in here and 1 card in here with different sizes of RAM on it, different types of chips on it. Not going to matter. This is what you go to Fry's and buy, the memory. If the CPU is reading it from the MMU, this can change. And you don't have to reinstall your operating system just because you added more memory on your system. So the concept of dynamic loading. So the routine is not loaded until it is actually called. So this is what we get with the Java runtime environment. Everything is dynamically loaded, as I mentioned before. So if we're not going to call it, which means we're not using it, we're not going to load it in memory. See, in the old days, in fact, this is sort of like how the operating system works. When the operating system loads up, it loads a bunch of stuff in memory, starting at the lower addresses. Half the stuff's probably not going to be used. Who knows? Maybe some of it will be used. But the concept is it's there just in case, which is kind of different in terms of the execution or in terms of utilizing the memory. It's kind of like how we go, you can go to Costco and buy, 50 rolls of toilet paper and go, well, I'm not going to use all of that this week, but I have extra, and I'm going to save it up. I'm going to use it in the future. So it's storage, long-term storage. But if I'm working at, maybe I have a small place and I don't have enough room to store 50 extra rolls of toilet paper, and it's going to get in the way. It's going to slow down my access to everything else. So dynamically loading would be only buying 1 roll of toilet paper and only loading that, and then every week going and buying another roll and another roll. More trips to the store. And in terms of an operating system, it's more trips to load as well. So you've got more processing, more loading and unloading when you're not loading as much than if you just took everything on your computer and loaded it up into memory. That was like solve everybody's problems. You never have to load it again. You're going to run out of space. You're not going to have enough. So dynamic loading is kind of an interesting concept in terms of an operating system design because there's different schemes to it. Just like people have different schemes to how they grocery shop, the operating system has different schemes to how it's going to load stuff into memory. In terms of dynamic loading, we're looking at a better memory space utilization. Unused routine is never loaded because it's never used. So unless you're going to call it, you're not going to load it. Useful when large amounts of code are needed to handle infrequent occurring cases. No special support is needed by the operating system. It's required to implement it through program design. The program itself decides when it's going to load something, which is kind of interesting. Operating systems only load what the program tells it to load. So if the program's not telling it to load it, it's never going to be loaded, essentially. So. Dynamic linking is different from loading. Loading is when you're going to put it in memory. And we haven't talked about taking it out of memory yet. But when are you going to put it in? That's the load part. The link part is, well, okay, so how are you going to get to it? How are you going to find it in memory? And in order to do that, we have to put some sort of a placeholder or some sort of something in our code to say, go and look for it here, go look for it there. So linking is postponed until the execution time itself. So the dynamically loading, this is going back to the concept between load time and run time. Load time is loading the concept, taking the object and loading it into memory. Linking or run time is connecting the dots so you can find the object that's loaded and then running it. So we have a small piece of code called a stub that's used to locate the appropriate memory resident library routine, and that's going to be in the program. So you've got a program is going to have a stub, and the stub is going to say, use that object. Sometimes it's a naming convention. In fact, that's how Java does it. You just name the object. Say, make a new instance of this object. Make a new instance of that object. And when it does that, it's essentially doing the equivalent of creating a stub. And it doesn't know where the object is. When you're writing the source code, it's never actually creating the object. When you run it, that's when it creates the object. So the stub replaces itself with the address of the routine, and it executes the routine, creates that. So the operating system needs to check if the routine is in the process's memory space, if it's in its address. Dynamically linking is particularly useful for libraries, and as I mentioned before, shared libraries. So it's also known as SO, or shared objects, or shared libraries, depending upon the operating system you're working with. So lo and behold, how do we take stuff out of memory? We swap it out. The interesting thing is we have, let's say we put 2 gigs of RAM on our computer. Those are physical memory, that's RAM, it's physical memory. Actually, let's give us 4, because 2 is not going to get us too far today. And let's say the operating system filled up 2 of that, and we have 2 gigs of it left. We're going to create 8 gigs of it from a logical perspective, let's say, in our main memory that we're going to use. The operating system is going to identify that and be able to expand it. Eventually, we're going to fill it up. When we fill it up, what do? Unload something. If we run out of memory, which happens all the time, actually, that's what we're supposed to do. If we're not running out of memory, you bought too much RAM. You got too much memory, it doesn't use it. Which is kind of funny because people go, well, why does buying physical memory and putting it on my computer, why does that make my operating system run faster? Well, it depends on what you're doing. There's a certain cases which you buy it, you put it on, you have no effect because you're never filling up your RAM. Until you start filling up your RAM, then you notice, oh, if I just added more RAM, if I added more space, I wouldn't have to swap. Swapping slows down the memory. Swapping is what makes your computer run slow. Swapping is needed. Swapping is needed because not everything can fit in memory. If you double-clicked on the old days, Microsoft Word 20 times, and you got 20 Word.exe files or whatever it's called loaded up into memory, well, when you go to double-click on the 21st, it's going to have to unload one of them. When it unloads it, it's not going to take it out of memory, it swaps it. So we have this thing called a backing store. And the backing store is a piece of your hard drive, actually. And here's the mystery of the hard drive. Your hard drive, when you buy your 300 gigabyte hard drive and you load it up into the operating system, you go, how come I only got 240 gigs? You ever notice, your hard drive space is never going to match what you see. In the old days, they used to say, that's because, operating system limitation. It can really only see 100 gigabytes or something, or it can only see certain. Not the case, really. Actually, it's reserved a piece of that hard drive because it wants to use it for something. One of the things that it uses it for is what's called the backing store, also sometimes referred to as a swap drive. So in Linux, you don't really have a backing store, you have a swap drive. Swap drive creates more RAM for you. And what ends up happening is instead of unloading it completely out of memory, because it might be needed, it takes and puts it on this backing store or on this swap drive and keeps it so they can load it back into memory. So we're constantly swapping stuff in and swapping stuff out, either on this swap drive or on this backing store, so that we don't have to load it fresh. So going back to what I said originally, and I said, well, what's the biggest difference in memory? The secondary storage is farthest away from the CPU. It takes the longest time to go get, so we're going to minimize the amount of time we're going to have to go do that. So we're going to go out and we have to pull something from the hard drive, from secondary storage, We're going to double click on that program. It's going to open it up. We're going to load everything in the memory. But after we've done that for a while, what ends up happening is we've got to go back and start using it again. So we create this swaps drive, this backing store, and when we run out of main memory, we put stuff to the backing store. Unless it's no longer being used, and we can unload it completely and don't even write it to the backing store. So a process can be swapped temporarily out of memory, and it can be put on the backing store and then brought back into memory for continued execution when it's needed. Which means we don't know when it's going to be needed, but we're going to locate it out there. This is expensive. This takes time. The more swapping your memory is doing, the more execution is going on, the more the CPU is working, and nothing's happening because the CPU is spent swapping processes in and out of memory, or swapping memory spaces in and out, and it's not executing any of your code while it's doing this, so it's wasted energy. So the backing store is the definition. It's a fast disk large enough to accommodate copies of the memory images for all users. Must provide direct access to these memory images. It's part of your hard drive space. That's what goes away when you install a new hard drive and you format it. Part of it's reserved for the backing store. So we have what's called a roll-in and a roll-out. So the roll-in, roll-out is the concept of swapping. So swapping variants used for priority-based scheduling algorithms. Low priority processes swapped out, so higher priority processes can be loaded in and executed. Because the program's never going to ask you. The program's not going to stop and say, well, I've run out of memory. What would you like me to swap out? It's going to either use a priority base to it, or it's going to use some sort of an algorithm that's internally programmed to decide what's the least recently used piece of memory. Let's take this out. We don't want to swap something out that we're going to need to swap back in. In theory, we're going to put something aside that's not really going to be used, or hasn't really been used. So the major part of the swap time is the transfer time. So the total transfer time is directly proportionate to the amount of memory that's being swapped out, obviously. The more you have to move, the longer it's going to take in terms of the time. Modified versions of swapping are found in many different operating systems, Unix, Linux, and Windows. The Windows system actually uses a swap drive. You can configure it in your advanced options, in your environment variables of the system, in your control panel. You can turn swapping on and off. And there's pros and cons to it, actually. You could have a situation in which your computer runs slower because when we have to go find something, depending upon how big the swap drive is, we have to go find it to bring it back into memory. We have a larger search space to go looking for it if we have a lot of swap drive space. However, the more swap drive space, the more swapping we can do. But it's only going to swap to a certain percentage of the allocated memory. So there's numbers they tell you, there's configurations. I think it's supposed to be 1/2 the size of your main memory. Your swap drive is supposed to be 1/2 or something like that. So if you don't follow the recommendations correctly and you just start creating stuff, you might actually create a situation in which your computer runs slower. So normally when you install a brand new Linux build, it's going to ask you, do you want to have a swap drive? And if you do have a swap drive, it's going to ask you, how big do you want it? Usually they tell you, make it half the size of the main memory. Don't go any bigger, because it might make your computer run too slow. So it defeats the purpose. So the system maintains what's called a ready queue as well. And the ready queue is a ready-to-run processes, which have memory images on the disk as well. So here's a systematic view of the swapping in terms of what I was describing. And over here is the backing store. It sort of looks like a hard drive. It looks like a little cylinder, actually. We have process number 1, we have process number 2 in here. And here we have our main memory, our logical or virtual, if you want to call it that, memory banks over here. And we have the operating system that's loaded up in the memory. Then we have the user space. We're going to, and let's say we only have enough room for one process. So we're going to swap out this process and swap this one in when we want to go from process 1 to process 2. Because both of them can't be loaded at the same time. Maybe only one of them can fit or something. This looks like both of them can fit, but theoretically the concept is to make room so we can load something else in. If we load it to the backing store, this is formatted just like this. So it's easier to put it here and then load it back in, swap it in and swap it out, than it is to just unload it completely. If you unloaded it completely, that's going to happen when the backing store fills up. and it can't load it here, it's going to be basically pulled out of memory completely, and then you have to go back to the hard drive, different format, read it, and it's slower. So the more you're loading fresh, the slower it's going to run, essentially. You can actually test this out on your computer, actually. I'm sure most of you probably have already noticed, the first time you run a program, generally takes the longest for it to run, and then you load it again, and it runs faster. Like the beginning, it has to load everything up. If it's already in memory, it's going to run faster when you go to access it because it doesn't have to go load it. And then if it sits there long enough, you fill up the RAM to the point where you run out of memory, then what's going to end up happening is, it's going to take even twice as long at that point. So you went with kind of slow to, really fast to, oh my god, it's really, really slow. And then most people reboot their computers at that point. They go, computer's running a bit slow. Because believe it or not, the longer you run your computer, the more memory leaks you're going to get, the more things are going to be swapped in and swapped out. Everything is fragmented. Everything is just out of order. Sometimes it's better to reboot your computer, sometimes just to clear the memory out. So let's talk about allocation. We haven't really talked about allocation yet. Allocation is where you're going to put process 1 and process 2. How are you going to allocate this space? And there's more than one way of allocating space, actually. We have contiguous allocation, where we start at block 0, and we go through block whatever, maximum number of blocks, and we allocate block by block. And we put processes in, we load them in right next to each other, back to back. So main memory usually is seen as two different partitions. We have resident operating system programs, usually held in the lower memory with an interrupt vector. And then we have the user programs that are held at the higher memory. So in this particular slide here, it's showing the operating system, and this is the lower bank, because this is upside down. This is 0 up here. I usually draw it the opposite way around, put the operating system on the bottom and load everything on top. But what we're looking at is filling up the banks. How are we going to fill up the banks more efficiently? So the relocator registers are used to protect the user processes from each other. So we set a register so we know when one process ends and the other one starts, so we can manage the memory that belongs to each one of the processes without writing or reading into each other's space. And then we can change the operating system code and data that's associated with it. So the base register contains the value of the smallest physical address. The limit register contains the range of the logical addresses. Each logical address must be less than the limit register, obviously. MMU manages everything dynamically. So the MMU is going to build it from at runtime while the program is running. So here's kind of like what it looks like. We have a hardware address protection with a base and a limit going on in this picture, where we have the CPU on one end. It looks for an address. Say, is it a base address? Can it find an address? No. And then we end up with this thing called a trap to the operating system, or a monitor that's correct, that says, it's not loaded into memory, or we can't find it, or there's an error, or something going on. If it does find the address, then we go from the base to the limit, and the base to the limit is going to give us our memory and tell us where in here. So you might think of this sort of like a lookup table. You could put the lookup table in the operating system and run it from a software perspective, or you could load it in hardware. So there's a lot of hardware support for the concept, and hardware support for the looking up of these particular addresses. But you have to get specific hardware for it. I'm going to zoom out a little bit on here so we can put the whole slide in the frame all at once. And then I'll zoom in over here in a few minutes. But in terms of the concept of contiguous allocation, we have multiple partitions that are created. And we are allocating them so they're all running back to back. And here's what happens. So we end up with this concept of the whole. Actually, here, I'll zoom in here. Playing around with my zoom today. Okay, so we have multiple partitions, and the whole is a block of available memory where we're going to load a process. And the holes are various different sizes and are scattered throughout the memory. This is why a lot of operating systems use the same size for each one of the processes. So if you use the same size for each one of the processes and you make it the size of the biggest process that can possibly happen, you have what's called internal fragmentation. Internal fragmentation is when you've allocated space and the space isn't being used. It's kind of like rations, If you say, okay, and we're going through the Great Depression and we're going to give one slice of bread to everybody, and everybody only gets one slice of bread. Well, there's people who might be hungrier than that one slice, and people may not even want their slice. And so that kind of creates a situation in which you have excess that's going to waste, like the people who don't want it, and it's not going to the processes that actually want it or that actually need it. If you say, okay, well then we're not going to make everybody the same size. Instead, we're going to have the processes only allocate memory, only take memory for what they need. We eliminate internal fragmentation completely, and at the same token we create what's called external fragmentation. Because external fragmentation says, and this is the example in the slide actually, when the hole is there and it's empty, but it's not big enough for the process, because another process came by and took a piece of the space, and then another process came by, and then that process left, and it left holes of different sizes. And so now this new process comes by and says, well, I need this space, and there's no hole big enough, and you can't combine the holes. So there's no hole big enough to be used to fill the space. And that's what's referred to as external fragmentation. You have memory, it's available, but you can't use it because it's scattered all over the place, and it's not contiguously allocated in a big enough chunk to actually load a process. Because the problem with contiguous allocation is it looks for a memory address at a base, and it goes to a limit. And it has to do it contiguously, one bank after the other. And if it can't find a hole that is of that particular size, even though you got 50 million holes in the system, it can't allocate it. So contiguous is very inefficient in terms of its allocation scheme. Very primitive, not really used anymore in terms of modern day operating systems. So when a process arrives, it is allocated memory from a hole large enough to accommodate it. The operating system maintains information about the allocated partitions and then the free partitions or the holes. So here we have an example of an operating system, process 5. Process 5 always stayed in. We had process 8 that came in. It was a little bigger than 5. We had 2 came in. And then 8 went away. And then we loaded 9. Oh, 9 fit just fine. And then we loaded 10 in there. But what if 8 came back? 8 wouldn't fit. So this is really what's referred to as external fragmentation that occurs. Classic problem with contiguous allocation. So if we're going to do contiguous allocation, we have to figure out, well, we have to have this algorithm. So we can figure out if, for example, if 9 comes in, how do we know we want to put 9 right here? Because if we put 9 here, it's not going to make it so 8 can come back anymore. And this hole is really bigger than this process actually needs. So now are we making it so that in the future we're not going to be able to allocate it correctly? It's kind of like rationing, if you think about it. So in terms of the allocation problem and the solution to it, to satisfy the request of the size n from a list of free blocks, because we're keeping track of how many blocks we have and how big they are, we can do one of 3 approaches: a first fit, a best fit, and a worst fit. And there's pros and cons to each one of these approaches, and this is what an operating system designer comes up with and configures for the operating system. This is one of the challenges of the memory management, actually. So first fit, the allocation of the first hole that is big enough to make it fit. And that's what we just saw, actually. We just saw first fit because 9 came in. It was the first hole available. Well, it was the only hole in the slide, but 9 went in there. Or we have the best fit, which allocates the smallest hole that is big enough. It's big enough, but it's the smallest hole. It's the best fit, which is in the perfect world. But you must search the entire list unless it's ordered by size. When is it ever going to be ordered by size? Probably never. So in order to find the best fit, you have to look at all of the different options and decide which one you want. It's going to take longer, not quite as efficient. Or we can do the worst fit. And here, the best fit's going to produce the smallest leftover hole. The worst fit's going to produce the largest leftover hole. In terms of the worst fit, allocate the largest hole, and then it must also search the entire list in order to do it. But we're going to take the biggest one instead of the smallest, or the best fit. Saves us a little bit of time, but we still have to search through the entire list. So first fit and best fit are better than worst fit in terms of the speed and storage utilization, as you possibly imagine. And here's our fragmentation terminology, and I kind of already explained it to you already, but I'll give you the terms for it. External fragmentation is the total memory space that exists to satisfy the request, but it's not contiguous. it's not all put together, so we can't find a block that's big enough, although we have all these little blocks. So it's kind of like when you go to the movie theater and you have 4 people, and you have one seat over here, one seat over there, one seat over there, and they're all spread out all over the place, but you all want to sit together. That's external fragmentation. So the movie theater is externally fragmented, and so then you ask people, can you get up, move a little, can you just move over one? And it corrects. So you have to have people get up and move to correct this fragmentation. The same thing in the operating system, which is how you can do what's called a compactation or compaction, or defrag. Let's call it defrag because that's what Windows calls it. It reduces the external fragmentation by shuffling the memory around. Shuffles the contents, places all of the free memory locations together in one large block. Makes the block big enough to hold 4 people. When we're talking about memory, we use the word compaction to talk about the memory compaction. When we're talking about hard drive space, the same concept is called defrag because we have a fragmented hard drive. When we defrag it, we're taking all of the programs and stuff that we have stored and we're moving them all together at the beginning of the disk so we don't have to travel as far to find these items when we go searching on that disk. And it frees up, makes things more accessible. Although secondary storage doesn't really there's not really a problem of fragmentation in secondary storage because we don't use contiguous allocation. So, internal fragmentation is where we have allocated memory and it might be slightly larger than the requested memory or what was needed. And the size difference in the memory is internal to the partition, to the process, and it's not being used. It's being wasted. It's like you took it because it was given to you, but you don't really need it, you're not using it, and you can't give it back. It's stuck inside your process space. So there's no cure for that. We can't just have processes give up memory. Instead, we do the opposite. We make sure that no other process can actually touch it or use it. So in terms of compactation, it's possible only if a relocation is dynamic and is done at execution time. One of the I/O problems, latch jobs in memory, well, it is involved in I/O. Do I/O only on the operating system buffers and stuff. So it's hard to do I/O on stuff while it's being moved around. So in theory, you don't want to move things. You don't want to compact things essentially that way. So to get rid of the concept of contiguous allocation, we have to come up with some different schemes because contiguous allocation is problematic. It's time-consuming to go allocate, even if you're doing a best fit or worst fit, biggest fit, any one of those fits. You're doing a calculation, you're running an algorithm to go find this piece of information. Instead, what we could do is take all the free frames, allocate them to pages, and then allocate the process as pages instead of frames. So paging solves the allocation by contiguous. The contiguous configuration solves that problem and creates a better abstraction of the memory. And pages are nothing more than an operating system abstraction. So logical addresses, a logical address space of the process can be non-contiguous in paging, and the process is allocated physical memory whenever the later is available. So we divide the physical memory out into fixed size blocks and we call them frames. And it might be, let's say, the size of power of 2, let's say between 512 bytes and 8,192 bytes or something. And the frame size is dependent upon your usage of the frames. So the operating system is deciding how big these frames are. We create the frames and we divide the logical memory into blocks of the same size called pages. Pages contain frames. So we create the frames out of the memory. We put them in pages and we allocate the pages. So we can keep track of all the free frames. And we just allocate them to pages and then pages get allocated to processes and then voila, no problem with contiguous memory allocation. It's non-contiguous now. So to run a program of size n pages, you need to find n free frames and load them into the program. So you set up what's called a page table. And the page table translates the logical to the physical address. And it gives you your mapping, essentially. And it creates internal fragmentation. If you're using, obviously it's going to lead to internal fragmentation, but there's no external. The internal is if all the frames are the same size and all the pages are the same size and you're allocating it pages, you're going to have some room that's not being used. You're going to have some memory that's left over. So the address translation scheme, so generated by the CPU, it's divided into two components, very similar to the contiguous allocation. Instead of starting at a base and going up to a limit, where we have a page number and then we have a page offset. Same concept though, it's just a measurement, and each page is going to be the same size. So the page number uses an index into the page table, which contains a base address for each one of the pages in memory. And then we have the page offset, which is combined with the base address to define the physical memory address to which the page is going to be in the memory management unit. So that's what's being sent to us from the memory management unit. So we have the page number, page offset. That's going to give us our mapping. Think of it sort of like a translation. So it's a translation between the logical to the physical that's being mapped for each one of the pages that we've configured. Let's see. Can I have my, what happened to the TA? Give me two minutes here. Actually, can you wait? Can you wait maybe about 15 minutes?
Yes.
Okay, come back in 15. Okay, perfect. All right. Sorry for the interruption. So the page table is keeping track of all of the pages, and the pages are being configured in terms of this address translation scheme. There's also paging hardware that we can install, or can't install. It actually has to be on the computer, which most of it, I will tell you, is done at a software level. In terms of the paging hardware, it's essentially the same concept, but it's implemented in hardware instead of from an operating system software perspective. So what we have here is the CPU. CPU has the logical addresses and the physical addresses, and it's the page table and the page that's giving us the abstraction of the translation between the two. And then this is essentially coming back out here, and all this stuff is coming from the memory management unit, which is kind of not shown on the picture, but it is in between here, because the physical address is actually coming from the memory management unit. And it's being translated via the page table, so the logical can go to the physical. And then it all maps out to our physical memory out here. And here's where F is over here, and here's where F is right in here. And the page table is the key to the whole schematic. And the page table is kind of an interesting concept because we can have more than one page table. We can have a main page table. We can also nest the page tables. And I'll have more about page tables in an upcoming lecture. But the page table is interesting. It's one of those kind of very useful data structures that can be created. So here's another view, and this is the paging model of the logical and the physical memory. And here's the logical over here, page 0, 1, 2, 3. We're defining these pages, and the pages contain frames. And our page table, and these are, let's call this an array, perhaps. It actually could be implemented in form of an array, but mostly it's going to be a hash table or something. So the page table as a data structure. This is a data structure. This is a logical concept. This is a physical concept. So the physical memory that's mapped to the logical memory. Logical memory says, take all these frames that we've got out here, these frame numbers that we've identified, and put them into pages. The zero entry, the first entry is number 1. Number 1 is page table number 1, and page number 1 out here is going to be mapped here. So we can know where these pages are in here by their mapping, and this is where it's going to tell us. So in terms of page table number 1, it's in frame 4. The first one, 0, is 1. We have 1 is 4. 2 is 3. What do we see here? Number 2 is in slot 3. So, and basically, we look at it. Basically, it's a lookup table, essentially, to find out the logical and map it to the physical. And here's a 32-bit memory map model in terms of another paging example, using logical memory that's mapped out in a certain number of bytes, and then we have the page table. So 0 is 5 over here, 1 is 6. If we go over here, we can map it out where here we get number 8, 9, 10, 11. This is going to be over here, I, J, K, L. It's going to be over here, M, N, L, P. This guy's over here, so number 8 is loaded up in the 8 bank. So. And essentially, we're just doing the translation. So, 1, 2, 3, 4. No, 5's down here. So, think of it like a lookup. lookup buffer. And interesting to note, we're looking at one page table in this example and one page table in this example doing a translation. We can have multiple page tables. We can have a page table per process. Because the process memory is divided out into banks, into sections, and it's allocated per process. So we could have a table over here where we have free frames, and we have free frames over here for another new process. And each process is keeping track of the free frames that it has, and it's allocating them out for pages when it needs to use page. And it can, have its own. We could have essentially another page table for each one of the processes. We could have one main page table that's organizing the entire sets of processes as well. What we're looking at here in this slide, I'm going to make it smaller so you can see it. Before the allocation and then after the allocation, we've populated a new process page table with the values after the pages have been allocated. So in terms of the processing that's going on. Here's the free frames here and that we're allocating. So we have 14 and 13 that are being allocated with the particular page numbers. Implementation of the page table. So as I mentioned before, we have a couple options. We can do it in hardware. We can also do it in software. It's more likely to have it seen done in software because we don't need specialized hardware for it. And not every operating system is actually going to support it. So the page table itself is kept in memory if it's implemented from a software perspective. And the page table registers points to the page table. And page table length register indicates the size of the page table because the registers themselves are going to be used in that capacity. So in this game, every data instruction access requires two memory accesses, one for the page table and one for the data and the instruction. So the two memory access problem can be solved by using a special fast lookup hardware called an associated memory or translation look-aside buffer. So as remember before, I kept calling it kind of a lookup scheme where we're looking up page table entries, and in the entries we've got a translation between the logical and the physical. Well, we can actually create a look-aside buffer for this, and the buffer is nothing more than a way of keeping track of the memory locations and using it as a fast index approach. So the transaction look-aside buffer, the associative memory, however you want to term it, is associated with the page table, and it provides us an index of fast lookup. Sometimes this can be implemented in hardware as well. It does not have to be implemented solely from a software perspective. So, some of the translation look-aside buffers are in software. Some of them are in hardware. Uniquely identifies, and some of them by definition uniquely identifies each process to provide address space protection for that particular process. So we're not going to write into memory that doesn't belong to the process. So in terms of associative memory, in terms of the concept, we have a memory configuration that provides a parallel search between the page number and the frame number. And we also have an address translation between page and offset. So if P is an associated register, we get frame number out of that one. Otherwise, we get the frame number from the page table in memory. So going back to the concept of the associative memory, think of it like an index. It's not called an index because it's not, everything in the page table is not in there. It's just an associative memory, kind of a way of looking it up quickly to save us some time, essentially. And both of these two concepts are implemented to save time, which is why they're implemented that way. And going back to what I said about the translation look-aside buffer, we can actually put it in hardware if we wanted to. If we put it in hardware, it's going to kind of look like this. Looks kind of just like the software, actually. Where we have the CPU, we have the logical address. The logical address is mapped to the physical address. And we have this look-aside buffer here that's in memory that's got the page number with the frame number. And we have the page table down here. And what we're looking at the slide is actually some new terminology called a hit and a miss. The hit is it in the page table, is it loaded into memory, or is it a miss? Meaning, is it not loaded? Is it in the backing store? Is it somewhere else? And do we have to load it? And that's actually referred to what's called a page fault. So when we go and we're the CPU and we're running a program and we know it's loaded in memory and we go looking in memory and we get a hit, it's easy. We just load it. I mean, it's already loaded, excuse me. We just run it. We just use it. When we get a miss, what ends up happening is it triggers what's called a page fault. A page fault, sort of a signal that says, hey, it's not really a fault. It's basically a wake up and says, hey, you need to go load this like from the backing store. It's not loaded into memory. We need to go find it. Page faults make the system run slower because it's not loaded into memory when we think it should have been loaded into memory. So now we have to go out and load it into memory. It's an extra step. We actually have to start over, load it into memory, and then go out and look for it again. The more we have to load into memory that's not loaded into memory, those page faults, make the system run slower. So in theory, what we're trying to do is minimize the number of page faults so that we can have most of the execution hopefully happening, most of the CPU time hopefully being used to process the information for the process and not to load memory in or swap memory out or something of that nature. So when we talk about memory, we talk about the effective access time. The effective access time, or EAT, if you want to describe it, is the associative lookup time, which is the time unit. So we assume the memory cycle is 1 nanosecond or microsecond, and what we can do is take and create what's called a hit ratio, which is the percentage of time that the page number is found in the associative memory. The ratio related to the number of the associated registers, perhaps. So if the hit ratio is calculated, we can come out with what's called the effective access time, which is going to be a calculation that's going to give us our average time it's going to take. And this basically computes sort of like a time estimate for based upon our hit ratio. How much time does it actually take to find something and access it when it's been loaded into memory? So the concept of memory protection is kind of a base concept that's used in this configuration. Memory protection is basically implemented by associating a protection bit with each one of the frames, and that was those little registers that we're setting. The registers are used for that. The protection bit says, hey, don't use me. I'm being accessed by somebody else. I belong to this process, or I belong to that process. So the page table can actually contain this information as well instead of using registers. And when we do that, we make a very sophisticated page table, because what we're setting is a valid or an invalid bit that's attached to the page table entry for each one of the pages that says, I'm currently being used, or I'm not being used by this process, I'm being used by another process, somebody else is using this bank, and I don't belong to this process. So valid basically indicates that the associative page is in the process's logical address space, and thus it's a legal page. An invalid bit indicates that the page is not in that process logical address space. If it's invalid, it's being used for somebody else. Somebody else loaded it up and is using that because it was sitting there empty, and we don't have any internal fragmentation going on. So, yeah, it was empty, it wasn't being used, so we're going to use it for something else. We're going to make use of it. Because we don't care about fragmentation, and we don't care about, contiguation. It's not contiguous, so we can use anything we want at any time. So the V and the I are normally the bits that are being set, and this is the page table. So now we have an extra entry in the page table that's keeping track of the valid or the invalid bit that's associated with the frame number that's associated with the page, or the frame, the page that we're allocating. So we have our pages, we have our page table that's associating each one of the pages with a valid or invalid. It tells us whether we've had a hit or a miss. The valid's going to be a hit, the invalid's going to be a miss. And we're going to go, oh, that's invalid. Can't load that. And then it's going to essentially give us that page fault that's going to tell us to go out and load it, essentially. So, shared pages. And shared pages is when we take the memory and we take that protection bit off and we allow multiple processes to look at that same piece of memory. Or we map the same memory to multiple processes for the purpose of allowing it to be shared. So shared code is one copy of the read-only reentry code that's shared among many different processes. Text editors, compilers, Windows operating systems, all a bunch of things actually use shared memory. Shared code must appear in the same location in the logical address space for all processes. Shared code is never moved. It's never swapped in or out either. So all that dynamic memory I talked about earlier in the beginning of this lecture is kind of the concept of the shared page. We put something in the memory, instead of swapping it in and swapping it out, worrying if it's valid or invalid or anything like that, we just access it. We just use it. So going back to the concept of the dynamically linked libraries and the shared objects and stuff, what we're looking at is maybe a print queue, or we're looking at operating system components or libraries, maybe for GUI or something, that's being shared by a bunch of different processes. Why keep loading and unloading it? Just load it once and link to it from an address perspective. So we have the private code and the data that's associated with it. So each process keeps a separate copy of the code and the data. The pages for the private code and the data can appear anywhere in the logical address space. So. And here's our shared page example where we've got the same data and memory is mapped to multiple different processes. So we have process 1 down here. We have the page table for process 1. We have process 2. We have page table for process 2. We have process 3. Page table for process 3. And remember, as I said before, we can have multiple different page tables for each one of these different processes if we want. And we might have ED1, 2, 3, data 1, ED1, 2, 3, data 1, and it's all using the same thing. So this is mapped to 3, to 3, to 3, to 4, to 6, to 1. It's mapped a little differently over here. 3 and 4 are the same. 6 is the same, actually. 2, the one on the end. The data is different. So this one's in 1, and the data over here is in 7, and the data over here is in 2. So number 3 is over here in 2. So as we want to keep the code the same, but we want to keep the data separate, let's say, for example, of these 3 different processes that are running. Which makes sense, because the 3 different processes. So you want their data to be kept separately from the actual code or whatever happens to be running in that process. So the structure of the page table comes in a lot of different things. We have a hierarchical page table, hash page tables, inverted page tables, which is kind of interesting. So in terms of the concept, hierarchical page tables, and there's really not that much to this outside of the description of what they're doing. I'm not going to get into the format of each one of them. That's something you would actually write yourself if you were actually implementing one of these. We could break up the logical address space into multiple different page tables. Simply technique to use. Usually a 2-level page table works, where we have a main table, and then in each side of the main tables, well, in the main table, we have these subtables, and the subtables are our page tables. And maybe the page tables in the subtables are the one for each process. So we can take all the processes, give them their own page table, stick all of those processes, maybe in process groups, and stick them in different page tables ranked from their different priorities. Yeah, perhaps. So let's see. My clock's on the wrong time. I looked at that and went, it can't be 5:45. It's 5:45. We're good. Okay, we're almost done with this data set, don't worry. I'm definitely thrown off by the time a few minutes ago here. Alright, so 2-level page table scheme, this is essentially what it's looking at in terms of the mapping. So in terms of the example and how it's implemented, logical addresses on a 32-bit machine, let's say for example with 1K page size, divided out, we have a page number consisting of 22 bits, a page offset of maybe 10 bits, and what we're going to do is essentially configure this so that we can keep track of the page tables inside of the page tables in terms of it. So since the page table is paged, the page number is further divided out to a 12 and a 10. It's inside of an offset. So it's just nothing more than adding another hierarchical level to it, another level of abstraction to break down the segments or the separation. So we have a displacement, we have a page number, and we have a page number 2, number 3, and with a page offset. So the information is basically kept in a hierarchy and divided out per process. In terms of the address translation scheme, it would go from the outer page table into the inner page table. So if we had logical address P1, and we had P1 was the outer page table, it would take us to P2, the page table, the page of the page table, and then we have the page of the page table again, or we have the address eventually. So it's basically going from each table to each inner table, from outer to inner, in terms of a search technique or a look-aside. So it's a 3-level paging scheme. We would have it broken out, so we had a second outer and a first outer, and then we have the inner, essentially. So we just have 2 more outers. You just keep adding out outers to it. So as an example, a 2-level might be 1 main table, keeping track of all the different processes, a a 3-level. It might be, let's say we have kernel level processes and then we have user level processes. So we can have a different priority at keeping track of different page tables that have different processes inside of each one of the page tables, perhaps. So it depends on the scheme of the page table in the operating system as to how it's going to be implemented. Hashed page tables. So common when the address space is big, essentially above a 32-bit. Virtual page number is hashed into a page table. The page table contains a chain of elements hashed to the same location. Great lookup scheme. Virtual page numbers are compared to the scheme, to the chain, searching the match. If the match is found, the corresponding physical frame is extracted from that. Here's an example. It's just the implementation is more of a hash structure versus a table. Just a standard lookup type of table. So the logical address here is a hash function is being used to operate on the hash table to do the translation for us, essentially, creating a more sophisticated, more streamlined process to it. Inverted page tables as another form. So one entry of each real page of memory is used. The entry consists of a virtual address, and the page is stored in that real memory location that's associated with it, with the information about the process that owns that particular page. It decreases memory needed to store the page table because you're only storing one of the addresses, well, one entry for each one of the real pages of memory. And so you're storing less, but increases time because you need to go search for the rest of the pages and references. So you're not storing as much information, so the page table is not taking up as much memory. But when you use it, it takes longer because you got to go find the information that's not given for you, that's not being stored. So it uses a hash table to limit the search to one, or at most a few different of the page table entries. So. And here's the sample implementation of the inverted page table, storing a little bit less information. So it goes through, finds the logical, comes down, does a little search. After the search, it comes back and populates it out with the physical address. So I can fill in the pieces. Now we have the concept of segmentation. So we all know what paging is, hopefully, in terms of the concept. Segmentation is interesting. It's sort of like paging, but instead of breaking things out into frames and pages, we're doing it into program segments. So the memory management scheme that supports the user's view of memory. What do we think about memory? We think about main, procedures, functions, classes, objects, all sorts of different programming constructs. So the program is a collection of segments, and the segment is the logical unit. So a segment can be an object, a block, a stack, a symbol, an array. Anything that would be kind of considered in terms of a segment of the program. And that abstraction is, again, another abstraction that's created by the programmer or the user versus the program. So here's the user's view of the program. In the program, we have this logical address space, and inside we have the subroutines, the stack, the symbol sets. This is a function, square root, main program. So segmentation is all the little pieces. And we use segmentation in terms of those DLLs, if you think about it. The DLL is going to be a dynamically linked library to perhaps give you printing functions or to give you scanner functions or something. And that's going to be a separate little piece of a program unit that's linked. It's linked at runtime or load time. And it's a segmentation concept, actually. So our logical view of the segmentation, here's our user space. And again, we're taking 1, 2, 3, 4 of different segment sizes, and we're putting them into memory, and we're storing them, and accessing them from the main memory of the program. So here's our physical memory space that's allocated per our segments. This is nothing more than kind of a terminology that's being used, segmentation. So when we get a segmentation fault error, it usually comes from a programming language syntax that comes out and says, well, we looked for number 4, but number 4 wasn't there. So we usually get a fault. Instead of a page fault, we got a segmentation fault, which you'd think would be the same thing, but the program's got to load it up. So we loaded an object, then we deleted the object, then we tried to call the object again. That's going to cause a segmentation fault. So when you start programming with dynamic memory, you start creating objects, you start using new and delete, like with C and C++, you're going to get a segmentation fault when you've loaded something in the memory and then you deleted it and then you went and tried to access it again. And it couldn't find it, so it generated a segmentation fault instead of a page fault. If you're on the operating system, you're going to get a page fault because it's a page that's loaded into memory from a paging scheme versus a segmentation scheme. So terminology is associated with the abstract concept of how you're describing it. So, segmentation architecture, the logical program consists of multiple tuplets, pieces in terms of rows. Think of a tuplet like a row. Segmentation number, the offset number. We can have, just like we have a page table, we can have a segment table. And the segment table maps two-dimensional physical addresses with each one of the table entries, and it's the same as a page table. We have a base and the limit that we're going to use. And we can still have the same concepts of a translation look-aside buffer. We can have a segment table base register and a segment table length register, and we can create this look-aside buffer concept to look up segments instead of pages, essentially, in terms of the translation. So we can have protection on that as well. And the segmentation is a kind of an interesting thing. It's not a common operating system implementation. Most operating systems of today are using more of a page component, a page kind of concept. So segmentation is really just a user mode abstraction of the same concept in a lot of ways. In terms of the protection feature, with every one of the entries, we can keep a valid bit, an invalid bit, a read, write, and execute privilege in terms of the memory that's being used. And the protection bit that's associated with the segments, code sharing might occur with segment levels, perhaps. And since the segments vary in length, memory allocation is dynamically stored. So we have dynamically allocated problem that might come out of that. And a segmentation example shown in this diagram here. This diagram here has segmentation hardware, just like we had page hardware. We could have paging hardware, we have segmentation hardware, why not? Where the CPU is going to look here, and we got a trap, because we have an addressing error, it's not loaded into memory. So it comes up here, and we have a segmentation table that's going to provide the translation for us to come back down here and look in the physical memory. So if it comes up here and doesn't find it, it's going to generate a trap. Trap's kind of like a page fault, so memory trap. Actually, a trap is a software level interrupt. So instead of the hardware, it's a software level. It's a trigger to the operating system, to the kernel, that, hey, you know what? You think it's in memory, but it's not. We can't find it, so we can't load it. If you can't find it in the segmentation table or in the page table, it's not loaded. Or if it is loaded, we don't know where it is. We've lost track of it. Somebody didn't update the page table correctly. An example of segmentation is we have a bunch of these segments over here, subroutines, stacks, symbol tables, a bunch of stuff over here. These are program units. And we have the segmentation table that's providing us the lookup, and we have the main memory over here. So hopefully you can walk away with the concept of what is the segmentation table, what is the page table doing. It's providing the lookup, it's providing the translation, it's keeping track. And this is stored in memory. All this stuff is stored in memory. So that's the other common misperception is, people go, well, where is that? Is it on the hard drive? The big picture is it's all memory. In fact, the operating system itself is nothing more than memory configured on top of memory. So last but not least, the example of the Intel Pentium in terms of its implementation supports both segmentation and segmentation with paging. So the concept from an abstract level is actually incorporated. The CPU generates the logical addresses, and it's given a segmentation unit. It's given to the segmentation unit, which produces linear addresses. Linear addresses are given to the paging unit, which generates the physical address in memory. So paging units forms an equivalent to the MMU. So with segmentation, we're kind of, we're doing a similar thing, but from a slightly different abstraction. So logical to the physical address translation in the Pentium is an example. CPU looks for the logical address, goes to the segmentation unit, finds the linear address, looks at the paging unit, finds the physical location of it, and goes out and loads it up into memory. So from a Pentium concept, in terms of modern day computing, segmentation and paging are both used in unison. Because if you think about the concept, without segmentation unit, you can't have dynamically linked objects, libraries, and things, because nothing's separated out. You're just talking about pages and program segments, processes. We're talking about pages, page tables. We start talking about program units and loading in libraries and reusing code and only loading something once and dynamically calling it, we actually have to think of it from a segmentation perspective. Otherwise, we can't see the program units. How do we know what this print queue concept is? It's a segmentation concept. That's what it is, really. And in terms of the Pentium segmentation in this little scheme here, this is our logical address, our selector with our offset. And we have our descriptor table down here where we have a segment descriptor, something identifying the segment in the scheme and then providing our linear address that's associated with it. So looking it up, essentially a segmentation table perspective, looking it up and finding out which we've got. Here's a Pentium paging architecture where we have a page directory. And the page directory has a page table, and inside of the page tables we've got the offsets. We can nest them, we can have a hierarchical page table with this as well. But all memory is organized with page tables or segmentation tables in terms of the concept. Our linear address in Linux, it's just broken up a little bit more into pieces, broken up into 4 layers, 4 parts instead of 2, where we've got a global directory, a middle directory, a page table, and an offset, not necessarily using segmentation. So, in terms of a 3-level paging in Linux, we've got the global, the middle, the table, the page. And think of this more like a hierarchical system where the pages have the frames, the middle directory has the pages, the global directory has the directory of the pages, essentially. So, and we use the information in terms of, we create some complex data structures to keep track of all of the information that's being stored in these tables. And these are nothing more than abstractions of tables that we're going to look at. So, all right, so that was the end of Chapter 8, and everything you ever wanted to know about the concept of main memory in terms of how it's configured, how logical memory or virtual memory is different from physical memory, how memory is organized and used. We've got more concepts to talk about. Paging. Next time we come, I'm going to show you some different algorithms for paging, allocating frames to pages. Also for a few more memory management configurations. These were the basic components that were discussed in Chapter 8, which is kind of like the basic foundational material. It's kind of like the vocabulary and the basic concepts from an abstract perspective. So next time we'll look at paging, and then we'll look at a little bit more about virtual memory as well. So unless we have any questions, comments, or concerns, we are done for today. Nope, we're done. Okay, thank you all. See you next time.